Hello, and welcome to Classical Mathematical Finance. So, of course, as you know, mathematical finance. So, of course, as you know, this class is completely asynchronous, which means that we'll be doing everything online and we will not be meeting at any particular time. Instead, all the lectures will be recorded and posted on Blackboard. Um, in fact, let's go look at Blackboard for a second so you can see what's already there. So what I've posted at the moment, and I'll of course continue populating this with the course content. We do have a syllabus, which we'll go over in a minute. The first section that we'll be considering, which is the time value of money. And then there's a corresponding spreadsheet with Excel examples to help us understand what we're doing in section 1. So anyway, let's go visit the syllabus and take a look, and you'll see that we have all the information you need to get in touch with me, Alan Anderson, PhD. And you can see there's my phone number. You've got my Fairfield email address. It does specifically tell us here that this is an asynchronous and online course. And so the course dates, officially this class starts on Tuesday the 1st, but at the moment, the Blackboard is already open, so you can go in there and download your materials and watch your videos as soon as you have an opportunity. The class will end in the middle of August, and all the assignments will be done through Excel spreadsheets, as it turns out. We won't have any exams as such. In fact, all that discussion is down here somewhere. But office hours, we can have office hours if you want, but what has to happen is it's going to be done through the Zoom system, which is what we're using right now. And that means that you can just send me an email and ask for office hours, and then we can figure out a time when it's convenient for both of us, and then we can have a session as you see fit. Either that, or you can simply send me emails and I'll respond to them directly. Now, here in the syllabus, it talks about what's going on in this course. This is an introduction to mathematical finance. Sometimes it's called financial engineering. It has other equivalent names, but basically what we're focusing our attention on is the pricing of different types of securities in the marketplace and the strategies that are used to hedge risk with these different derivative securities. But we're also looking at basic concepts like the time value of money. We're looking at bond pricing. We're looking at stock pricing. We're looking at forwards and futures. We're looking at options. And then we're going to spend a lot of time analyzing the Black-Scholes option pricing model, along with the corresponding risk measures that can be derived from it. And so it's a very intense course, and very important, though, because if you wanted to work on Wall Street, for example, and you wanted to be a quant of some kind, you'd be expected to have this background, the math and the programming skills that we'll be developing. And you would also be expected to have the knowledge of the financial products. So it's a very, very interesting area of study, to say the least. And it's really, in terms of mathematics, it's still in a relatively early stage because a lot of it is based on math that was produced in the 1950s by a Japanese mathematician named Ito. And so we'll see that as we go along. A lot of the results, especially in the option pricing sections, are based on what is called Ito calculus. Some of the rest of this material is much, much older. I mean, clearly the time value of money is a very fundamental concept in the financial markets. That's been around for, God only knows how many years that's been around. But some of these securities that we'll see later on in the course, the options in particular, have really only been traded in the United States for a relatively short period of time. And that's partially because of their complexity. It took a long time before it became possible to come up with a pricing model for options. And that really, as you can probably imagine, sort of restricted their implementation. So we're going to see how options are priced. And surprisingly enough, we'll be able to do all of this in Excel. Although we're not just going to use Excel itself, we're going to use a programming language that's attached to Excel called VBA, or Visual Basic for Application. So for certain things, Excel is fine. But for other types of applications, it's not really quite what we need. Luckily, it does come with this full-blown programming language, and it always has since the first days of Excel. It's just that a lot of people don't even realize it's in there. So at some point, we'll introduce this language, and you'll see how it can make things a lot quicker for us when we try to come up with pricing models for these different securities that we'll be studying. Anyway, let's see, what key details do we need to know? Well, first of all, as I started to say earlier, this is a little bit different than what you're used to in the sense that there's not going to be any actual exams. Instead, all of the assignments, the programming assignments, which will be done in Excel, will represent the entire grade for this class. Okay, because the focus here is to try to learn how the instruments work and also how to price them, and that's best done in Excel. So yeah, it wouldn't make any sense to have tests in a class like this. So the books are listed here. Now, this book is one that you might just have a little trouble finding it. I don't think it's still in print, but I think you can get a copy of it. There was only the one edition. Let's see if Amazon still has it. This is where I got my copy, but it was a long time ago. What do you know? They still have it. $94. That's not bad for a hardcover. The reason why you might want to have, yeah, there it is. I bought it in 2002. God, that shows you how time flies, huh? The beauty of this book is that it not only explains the models themselves in very great detail, but it also has not code, but algorithms. In other words, they explain to you in very great detail how you would price these different securities or carry out all these different numerical techniques in any programming language. The book itself is not based on VBA. What they're saying is, listen, here's something we need to accomplish, and here are the steps that you would follow to get to your result. And so those steps are so well written and so detailed that it is possible to implement these models with many different programming languages. Now, now what's interesting about all of this is that at this point in time, and I've never tried to experiment with this myself, but from what I've been told, if you have enough information, enough detailed information, it may actually be possible for AI to help with the programming process. Okay. And so this is something I know very little about, but it might be interesting to find out if it actually works or not. But in the meantime, we're going to learn how to write VBA code, and we're going to understand the commands. We're going to look at the structure of the language. We're going to learn the things that we need to know to implement it correctly. And the nice thing about VBA is that since it's already built into Excel, it's easy to read data into and out of it directly from an Excel spreadsheet. And here's the other thing I wanted to investigate. I haven't had a chance yet. Very recently, Excel suddenly started offering the ability to use Python code. And I don't understand or how that's going to work. But if you look in the menus here, it specifically mentions it in some of these tabs. Now, the thing about Python is VBA has been around for a very long time. In fact, it was probably written, for sure, it was available in the earliest versions of Excel in the late 70s. It was probably already around before that. The good thing about VBA was that it was meant to replicate English statements in a way that other programming languages did not. Many programming languages were very mysterious and very cryptic and hard to follow the reasoning and the logic. So VBA was designed to be a way of learning how to program without getting bogged down with complicated instructions. Now, Python is like that in a lot of ways. It is also very English-like. The difference is that it is a much newer language, which means it's much more flexible and powerful. And it's a kind of thing where, it's heavily used in the financial services industry because of its power and flexibility. And another advantage to it is that it's actually available for download completely free, as opposed to, let's say, one of the more best known scientific programming languages, which is MATLAB, which is horrendously expensive. And I don't know how they get away with it because, it's getting to the point where, for the most part, we're not paying for any of the software anymore. We're getting subscriptions. So anyway, this is what caught my eye. Supposedly Python is here. Um, I think it would be interesting to see if we could, during the course of the semester, see how maybe some of these programs could also be written in Python instead of just VBA, just to get a feel for how this works, because Python is a hugely important language at this point in time. So I don't know how sophisticated this is, but it says here that you can insert Python formulas. So I'm not sure if that's all that it can do, but this is the kind of thing I think would be worth investigating. But in the meantime, we can still use our VBA. The VBA still comes as a standard part of the language. That will never change. But I do think that whenever possible, we should try to at least figure out how to maybe also use Python if it can be done. I mean, I just don't know how much Python is actually in here. That is something that I think is definitely worth investigating. So in other words, we have a lot more tools available to us than we did even 10 years ago. And so, but we're going to do everything the old-fashioned way first by writing out code and running it and making sure we're getting the right results. And then we can feel free to experiment with more sophisticated techniques like, let's say, Python or even artificial intelligence, just to see what happens. In fact, you could easily imagine writing a book about this. Like, well, if you wanted to do this in Excel, here's what you do in Python, and here's what you would do in VBA, and here's how AI would handle it. So anyway, so we'll have a lot of fun with this. But first, we have to learn the basic concepts. And we're going to go to the very beginning and start with our discussion about the time value of money, which is not conceptually very difficult, but it is the foundation of everything that follows. And in fact, it's the kind of thing you would often learn in your first finance course in an MBA program, because it's awfully important in every area of finance, like banking and, investments and, management and whatever the case may be. And so that's where we're going to start. And now, luckily for us, a lot of what we need is already built into Excel. And if you happen to have one of these TI-84s, which is, in my opinion, the best calculator on the market, but that's just my opinion. What I'll do as we go along is I will show you the commands you would use to get your results out of this TI-84. Okay, it's a very powerful calculator, and you might be surprised to learn that it does have time value of money concepts built into it. It's perceived as an engineering type calculator, but in reality, it really does have a little bit of everything, including calculus, by the way. If you I mean, there's so much stuff in this calculator. It's just, I never stop learning about it. So, all right. Anyway, back to the syllabus for a minute. We're going to look at the time value of money. Then we're going to move on to the yield to maturity, internal rate of return, which gets us into the pricing of bonds. And then we'll be looking at interest rate risk and how that's measured. And then we're going to see the different ways interest rates can be defined. And then we can start our discussion about derivative securities. And so we'll start with the simplest ones, which are forwards and futures. We're going to understand their key properties. We're going to understand what they're used for and how, and why market participants use them. And then we're going to go to the top of the mountain, let's say, options, which are by far the most complicated and powerful of all the derivative securities. And we're going to learn how to price them properly. We're going to look at their different how they're structured. We're going to understand how they're used for hedging purposes, but also for how they can be used for speculative purposes. We're going to see how the relationships between options are determined in the marketplace. We're going to learn about something called stochastic calculus, the Ito calculus. It's the same thing. And we're going to learn about risk management techniques using options. And at the end, we'll be looking at a very powerful and sophisticated model for pricing what are called American options. And then that will be the end of that. So by the time we're done, you'll have a lot of good background in mathematical finance and some programming skills and some Excel skills. And it will be very, very helpful to you. Now, one more thing I overlooked. I went right past it, but the derivatives models book is here. They do have it. I was a little surprised to hear that because it's such an old book. But look at that. It's you figure they sometimes when they have something that is of limited availability, they'll offer to sell it to you through a third party vendor. But it doesn't look like it. No, they've got it right there. It's so funny how it apparently never went out of print, but they never updated it either. That's kind of strange. All right. Well, anyway, now the other book that I'm going to recommend, but is not really necessary, is the classic derivatives textbook, Futures, Options, and Other Derivatives by John Hull. This is it. If you're going to have a book on your library that about derivative securities, this is the one. This is the gold standard. It's been around since, by now, it must be at least 20 years since the first edition came out. And Hull teaches, I'm not sure if he's retired or not, but he was at the University of Toronto. He must have made a fortune off this book because everybody owns it. Let me just see. The only problem is if he is retired, it's possible they haven't updated it in a while. But see, there's also a lot of different editions of it. But it has everything. It's like an encyclopedia of derivative securities. And what's great about this whole setup here is that the other book, Clelau and Strickland, their book is based on Hull's approach. In other words, they're using his models and his notation to get to the results that we need. The only thing is the value they're adding is the instructions for implementing these models on a computer. Okay, so Hull's book doesn't have that. It's more of a very hardcore MBA book. Very hardcore MBA book. But he does not quite get around to saying, well, if you want to write code to do this, here are the exact steps you need. He explains it very well, but he doesn't give you actual code or algorithms like this book does. So the two of them together are a very potent combination, and it makes it very simple to implement these models on the computer, as we discussed earlier. So these are the two that you probably should have. All right. So all the notes that you'll see in Blackboard, I wrote them based on Hull's book because it's my favorite. So, it looks like I accidentally put something in here twice. Let me just take care of that. So section 1, time value money, what you see here is the notes, the slides that I wrote, and there's an Excel spreadsheet in here that we're going to use to understand what we were doing in this section. So I added this later, and I didn't realize I have a duplication here. All right. Now, by the way, I just want to mention one other thing here. You notice how I've got the PowerPoint slide and I've got the PDF. The reason for that is because if you're using a Mac, sometimes what will happen is I've written all these slides on PC, and sometimes equations and symbols and graphs don't translate well from one platform to the other. So if you find that on the PowerPoint slides, something doesn't look right, you can look at the PDF version, which is essentially just a photograph of what I've done in the PPTX anyway. So that's why there's two versions in there, just in case you're using a Mac. All right, so enough talk. Let's get started with the notes. And so let's open up the spreadsheet. Well, the spreadsheet's open. Here are my notes. And you can see we're going to start with the time value of money. It couldn't be more important. This, like I said, this is really the heart and soul of what finance is all about. So basically what it refers to is the idea, very simple idea, that a dollar received today is more valuable than receiving a dollar in the future. Why is that? Because the sooner you receive that dollar, the sooner you can invest it and earn interest. So interest is what's going to determine how valuable a cash flow received in the future is. So the time value of money will help us understand how to compare the cash flows received at different points in time. So we're going to have four basic concepts here. The future value of a sum, which means a one-time only payment. The present value of a sum, again, it's a one-time only payment. The future value of an annuity, which is a repeated series of equal cash flows. And the present value of annuity, okay. So future value in a nutshell means how much is an investment worth in the future. The present value is the opposite. It means how much will a future investment be worth to us today? Okay, so we can apply it to a single sum or an entire annuity. Many financial products are structured as annuities, which is why this is so important. So we're going to do this in a few different ways. We're going to see how to do this algebraically, and then we're going to see how to do this with Excel. Okay, and then we can also see how it's done on the TI-84 if you're interested. You don't have to do it, but I think it's a good idea if you own one to learn how to use the financial applications built into it. And yes, they're in there. You may not have known it, but they're in there. All right, so we'll start with the future value of a sum. Now, if a sum is invested today, it will earn interest and increase in value over time, of course. The value that it grows to is known as its future value. Computing the future value of a sum is referred to as compounding. Okay, so yeah, I mean, you can imagine how this would work. Let me write this out on a separate diagram. So we often use a special diagram, which is called a timeline, to illustrate these types of time value money problems. All right, so I'll create a separate document here so I can make more notes, and I'll post these later on when we're done. So, for example, let's say and by the way, on this timeline, we often show on, it doesn't really matter whether it's the top or the bottom. I usually put the time in the bottom. Those numbers represent time, meaning that this is today. This is 1 year in the future. And this is 2 years in the future. And these don't have to be years. They could be months or days, whatever the case may be. So on the top of the line, we'll have cash flows. Now, the important detail here is that cash flows that are coming into our pockets are shown as a positive number. The ones that are going out of our pockets are shown as a negative number. So today, imagine I put $1,000 in the bank. So I'll show that with a negative number. And then in 2 years, it's worth, let's say, $11.50. Okay, so Now we're assuming that I left the money there the whole time. I never took out any of it in between. So what I can say here in this example is that 1150 is the future value of $1,000. And we can also turn that around and say that 1,000 is the present value of 1150. Okay. So what that means then is that in principle, if you had your choice, you would be indifferent between receiving $1,000 now or waiting 2 years to receive 1150, because in investment terms, it's the same thing. Okay. So the question is, how do you go from 1,000 to 1150? Well, in order to answer that question, we need to know the rate of interest, right? So you'll see interest rates are going to be the driver of everything in this section. Okay. Now, interest rates, as you know, are determined in the marketplace through the activity of buyers and lenders. And it's a very complex topic, and we'll be discussing a lot of it as we go along. But we're going to make some simplifying assumptions here. We're going to assume that I can put my money in some investment, let's say it's a bank account, and get some rate of interest, and that will let me determine how much I'll have in the future. So in this case, we're going to see our first equation of the course. Let's see what this is all about. All right, so well, two of these should be pretty straightforward. And the notation here, by the way, is I'm pretty sure, if I remember correctly, this is based on Hull's book. FV is future value. E is the present value. R is the rate of interest. And N is the time at, over which P is invested. And that it might be in years, but it doesn't have to be. Okay. So the interest rate, by the way, just as an aside, interest rates are always quoted on an annual basis, which means if it says 3%, it means 3% per year. All right, so that's understood. Also, in an algebraic formula like this, we always represent interest rates as a decimal in algebraic formulas like this one. So in other words, 3% would be written as 0.03. Okay. These formulas, any formula you run into in finance, it is not going to accept a whole number like 3 for 3%. It's going to ask you for 0.03. So let's just use a quick example. Let's say, suppose that $1,000 is invested. Let's say for 5 years at a rate of 4% per year. So you put the money in the bank, you leave it there for 5 years. At the end of 5 years, you come into the bank and say, how much do I have? And they'll look at it and say, oh, here's how much you have. Here's your balance. That would be the future value of the $1,000 invested today for 5 years at a rate of 4%. So based on our formula, oops, so it's 1.04, 1 plus the rate of interest. The rate of interest will be expressed as a decimal of 0.04. We add 1 to that. The exponent is 5. And let's see. Now, for this, you will need a calculator. And of course, the answer will be rounded to dollars and cents. That's the future value. So in other words, in 5 years, my balance will be 1216.65. And of course, it should be obvious that of this 216.65 is my total interest. Okay, so now it turns out we might as well discuss this now because it's going to be important. There are two basic kinds of interest that I've just earned. Okay, it's true that I made 216.65, but we can break this down into two other types of interest. Interest can be earned from two different types of interest. Let's put it that way. We have what's called simple interest, which is interest on the invested principal. And we have something called compound interest, which is interest on interest. Now, what does that mean? All right, well, what's going to happen is that every year that goes by, in fact, I'll tell you what, let's do this. Let's figure out, although this might take a while, I guess, how much interest we're earning every year from this account. All right, so let's try this real fast. At the end of the first year, we're going to have 1,000 times 1.04, because remember, it's 4% per year. Okay. Now, clearly, $40 here is our total interest. Because all 4% of that was based on the original principal, all 40 of that is what we're going to call simple interest. There's no compound interest. Not yet. Now, at the end of the second year, we're earning a 4% return, not just on the original $1,000, but on 1,000 plus the $40 interest we earned in year one. So that's going to bring my balance to $1081.60. So if you notice, during the first year, I earned $40 worth of interest. During the second year, I earned $41.60. Where did that extra amount come from? Good question. So altogether, I've earned $81.60 in total interest. Now, 4% for 2 years times the original principal of $1,000 is $80. That is simple interest. And that will never change. In other words, I'm earning $40 a year in simple interest, which implies that the rest is what we're going to call our compound interest. Or if you're not sure, what you can also do is think of it as 4% of 40, the interest earned during year one, is, as you'll see in a second, what do you know? 4160, which means 1.60 is the interest. And it is specifically the compound interest. So that last $1.60 is based on the $40 of interest we earned during year one. Altogether, we have $80 worth of compound interest. So let's look at year three. Well, I'm sure you can guess where this is going. We're going to have another $40 in simple interest, but we're going to have even more compound interest. So our new balance is 1124.86. And now we're running desperately short on space here, but I want you to notice that of this 124.86 in total interest, 40 times 3 equals 120 is our simple interest. And the rest is our compound interest. So let's just carry on. Let's go all the way out to year 5. We have 1,000, as we just saw, brings us to 1216.65. Now, how much simple interest does that represent? Remember, it was $40 a year, 200. Oh, actually, what I should have done, hold on one second. Is it just right here, the total interest is, of course, 216.65 because we started with 1,000. The rest must be the interest. So the simple, as we've discussed, is 200 because it's $40 a year for 5 years. The rest is the difference, which is 1665. Now you're probably saying, well, that's not much, it's it's not that it's not worth worrying about, but it's a very small percentage of the total. But what's going to happen here is that over time, if you were to plot out the simple and compound interest as the years go by, and as years in this case, their simple interest grows like this. It's a linear function. The compound interest, on the other hand, accelerates over time. In fact, in the limit, we'll discuss this later on, but in the limit, it grows at an exponential rate. So if you're saving money for retirement, let's say you put money in the bank for 30 or 40 years, by the time you retire, the vast majority of that money will come from compound interest. Okay. As you leave the money long enough, it really grows very, very, very quickly, but it takes a long time to get to that point. So, no matter what investment we're making, it should be easy to determine, first of all, the future value. Now, of course, if you notice, this is a simple case, the interest is the same every year. That's not such a big deal. If you're investing your money in something like a certificate of deposit, which, if you don't know, it's a special type of savings account. Whoops, hold on. Oh, I just realized I never saved this document. I better do something about that right away. You know what's going to happen if I don't? My electricity will go out for 1/10 of a second and my work will be lost forever. So by the way, I'll be posting all this on a Blackboard when we're done. So if you miss something, you'll have a copy of this. Anyway, so yes. So compound interest, simple interest, total interest, those are three very important concepts for us to keep in mind when we analyze these investments. And so we can figure out the future value from this formula. The simple interest, it's just a question of multiplying out the percentage interest, the principal that we're multiplying it by, and then the number of years. So in other words, the simple interest using this notation would be P times R times N. That's all it is. Okay. Whatever's left over is your compound interest. All right. So this is a good start. Here's the example I had in the slides. We have the sum of $1,000 invested for 4 years at an annual rate of interest of 3%. What is the future value of the sum? All right, so we'll do the same thing. We have N is 4 years. 3 is the rate of interest, which you notice I've converted to a decimal. And then the principal or present value is $1,000. Multiply those out on your calculator, and you'll see that it's always rounded to dollars and cents. We end up with 1125.51. Now, you know how to determine how much of that is total interest, simple interest, compound interest. So I'll tell you what, let's figure that out right now. So first of all, let me add some page numbers here. All right, so remember the details we had. So you can take that out, you can take your calculator and solve for that directly. And you'll get, yes, 1125.51. Now, of course, obviously, the last 125.51 is your total interest. That's the easy part. So the total interest, it's going to be the future value minus the principal. Now, remember, I mentioned earlier that the simple interest is the principal times the rate times the number of years, 1,000 times 0.03 times 4, $120. So whatever's left over must be the compound interest. Move that back. So the difference, so I put the little negative there. The compound interest is the rest, which is 551. And again, for such a short time frame, the vast majority of this interest is simple interest, but that will change over time. After enough time goes by, eventually it'll be the compound interest, which is the majority of the rate of return. Okay. And then here, it discusses the difference between the two. Now, what if we want to do this in reverse? imagine yourself saying I need to save $10,000 in 4 years to buy my dream car or something like that. The question is, how much would you have to put in the bank now in order to ensure that you have the right amount in the future? Another way of thinking about it is that if I had a choice between receiving $1,000 in the future and let's say 850 today, would that be which one would I pick? Or at what point, how much would I have to receive today to be indifferent between having that sum now and $1,000 in the future? So what we're going to do is calculate the so-called present value of a sum. And it turns out that this is awfully important because all securities in the marketplace, stocks, bonds, whatever you may be thinking about, ultimately their value is nothing but the present value of their future cash flows. So you can see why I said before, this is really the foundation of all of finance right here. The time value of money is the bedrock on which finance sits. Okay. So algebraically, you can probably guess what's going to happen. We're going to invert this formula and solve for P. All right, make this just a little bit bigger. So if you rearrange this algebraically, this implies that P equals FV over 1 plus R to the n power. All right, so let's look at the case in front of us. Let's say we want to know how much would we have to put in a bank now. It pays an annual rate of interest of 5% in order to be worth $1,000 in 3 years. So it's a 3-year investment. We're aiming for $1,000 in 3 years. That's our future value. And then the rate of interest is 5%. So it's a simple matter of plugging this in. Whatever this number is, clearly it'll be less than $1,000. The question is how much less? It's 863.84. So that implies that over the next 3 years, I will be earning interest equal to the difference between these two. And that's going to be 126.16. Nope, it's 136.16. That's what I get for doing it in my head, I tell you. Okay, so that means by saving, I'm earning 136.16 worth of interest to guarantee that I'll have my $1,000 in 3 years. So, or think about it as in terms of investments, having 863.84 now is equivalent to having $1,000 in 3 years. And now one thing that we did not quite get around to analyzing is what happens when the interest rates change? What happens to the present and the future value? All right, so actually, I guess my intention is to have these sessions last for roughly an hour each. So I'll tell you what I'm going to do. Let me add this to the bottom here so we don't forget about it. What I'd like to be able to do is show you the relationship between the rate of interest and the present and future values. In fact, we could go into Excel and create a nice little chart so you can create a graph and see how these are affected by different interest rates. So how are PV and FE affected by interest rates? Well, you know what? Maybe we can do it right now. Hold on one second. This shouldn't take too long. Let's go back to the previous example for future value. N is 4, R is 3%, and P is 1,000. And the future value, we can do this algebraically, is P times 1 plus the rate of interest raised to the n power. And rounded to dollars and cents, as we saw, it's 11.2551. So what I'd like to do now is create an entire table of these results where only the interest rate is changing. Actually, I'll put R out here. R and P all right, it goes all the way up to 27. We don't really need that much. Let's stop it at 25%. And so I'll use that formula, FE, equals P over, P times 1 plus the rate of interest raised to the n power. And so what I'm going to do now is insert a graph. And you'll see that it's not a linear relationship. So in other words, as the interest rate goes up, that would be our independent variable, or X. The future value is the dependent variable, or Y. And if you notice, it's increasing, but not at a constant rate. It appears to have a first and second derivative that are both positive. Okay, so what about the present value? So the example on our slides is this. N is 3, future value is 1,000, and we're looking at a 5% rate of interest, and the PV turned out to be $863.84. So we're going to set up a similar chart here. Except this time, I'll reverse these two. So we'll let R be everything. We'll go up to 25%. N is 3. PFE is 1,000. So for this, we have 1,000 over 1 plus r raised to the n power. And then I'll grab these two columns. Well, that's strange. I guess it way it worked before. Oh, there. What was the holdup? So anyway, it goes down. That's the bottom line, but it's not a straight line, is it? It's curved. We'll discuss the consequences of that later on. It will be an important detail when we're looking at the management of interest rate risk. This relationship between prices and present values, sorry, rates and present and future values. All right, let's see. Just to be consistent, I'll call this future value. All right. So I think that was kind of helpful. So, Eric, yes, anyway, so we'll cut it off right here. The next time we'll just carry on with this first section. We've got a lot of material to cover here, by the way. We're going to introduce this concept of compounding frequency, which is a hugely important idea. So we'll save that for next time. And so we're getting into some very deep waters here, as you can imagine. So for the first session, that's quite enough, I think. So next time, we'll get involved in compounding frequency. So I'll see you then.